Hello all, this is Shrikant Umal. I am part of the US consulting group based in Silicon Valley. Today we are going to see a few items. The primary one is how can you build Qt without, in absence of Yocto based development environment. To begin with, these are the four topics that we are going to discuss. As I said, the primary focus would be on instructions about how to build Qt with a non-Yocto build environment. And then we would also touch upon what are the graphic backends and input handling choices available to us when we are working or developing an applications for an embedded platform, especially running Linux. And then we have this Qt Lite configuration tool using which we can build Qt binaries and we can scale them down. We can make them a bit light as compared to what they would be if we don't use this Qt Lite tool. And then I would briefly touch upon how to add a Qt recipe to your own Yocto build. So as you are aware, Qt already provides a standard distribution of our own, which is boot to Qt. But many times you would want to use the boot to Qt recipes in your Yocto build environments. So these are the four main points that we are going to go through. I'll start with building Qt for a non-Yocto build environment. Today I'm taking an example of a Raspberry Pi board. The reason being it's easy to put it together. Qt already offers a boot to Qt image for Raspberry Pi, but there are people who are using a development environment like Raspbian to run it on the Raspberry Pi. So I'm going to take that as an example. Raspbian doesn't have the latest Qt5 on it. It would have some variant of Qt5, but won't have the latest one. What I've done in this attempt is I have set up the development environment for Raspbian, and I'm building the latest Qt5 for it. Now, to begin with, these are the primary considerations I should be making. The first thing is I need to set up the build environment. Though I would be talking about my experience setting it up for Raspbian, this would be more or less applicable to other development environments as well. So the first thing I need to obtain is the development sysroot. Now this is a copy of the sysroot that would be actually running on your device, with additions of libraries and header files which you would require to develop any application for the device. It is not relevant. It's not specific to Qt. It's applicable to any simple application that you would want to run on that environment. And it would be handy, it would be useful if that development sysroot also contains the package config files. This is because the Qt configure script, which is the one that you run to configure Qt, would pick the dependencies looking at these package config files. And I would also talk about like what one should do in absence of these package config files. And then like on the embedded devices, these days we also target hardware acceleration. So many a times there would be some deviations where the platforms would be keeping their Easel or OpenGL libraries. The names might be different, so you need to check on those two. And then the second important part in this build environment is the cross-platform toolchain. What you need to do is you need to identify what are the optimal compilers and linker options for your targets, and then you would use them to create a Qt config. Now I'm going to show you the contents of the file that I had to put it together. So before you even start configuring Qt, you would have to look at this qmake.conf file. It could be found in Qt base megspecs devices folder. Usually, if the device is already supported by either by Qt company or by the open source community, you would find an entry for that device here. Many a times this file could be pretty old, and if there have been some changes, you would have to make some modifications to this file. There are multiple ways in which you can do it. You can create a copy of that folder and rename it to whatever you want it to be, and then edit the qmake.conf, or you can edit the existing qmake.conf by introducing some environment variables. I'll talk about that in a bit. So this qmake.file typically contains the build settings that you will be using. And if you remember from my earlier slide, when you put together the cross-compiler toolchain for your device, you had identified the optimal compiler flags and the linker flags and the location of the third-party libraries that Qt requires. So all this information has to be put together in a qmake.conf file. Then I would talk about the EGLFS hooks a bit later when I'm going to touch upon the graphic packings available to us. And the third point is, as I mentioned, references to device-specific libs. So if in absence of a package config, if you want the Qt configure to look into different places for the header files in the libs, this is the place where you can specify where to look at. And in the configuration, we have these three options: -device, -sysroot, and -device option. I have put a snapshot of a simple configure line in the same slide at the bottom of the slide. So if you see the device, the -device option refers to the location of the qmake.conf file that would be picked for building Qt. -device option is something is a variable that you would want to expose and then utilize it in the qmake.conf. So you can specify -device option multiple times. In this example, I'm using a variable cross-compile as an example to specify the prefix of my compiler, but it could be any variable that you want to refer inside qmake.conf. So it could be even if you want to specify your library and header paths, you can do that over here by introducing another variable of your own. Cross-compile is not a standard variable. It's a variable that we are typically using when we use to configure for embedded devices and for specifying the cross-compile toolchain. And then there is this option -sysroot. This should point to the development copy of the root file system that's on your host environment. So what it contains is the header files and the libraries that I spoke about in the earlier slide. And then obviously, if you are familiar with configuring Qt, you might have seen this minus prefix option. That's where you would want to keep your Qt build. Now, in this case, when you would configure Qt, it's going to put it, create this path inside the rootfs, which was passed as a -sysroot, and when you would say make install, the result of your build is going to be copied in that location. Now I'm going to show you what I did in my attempt to build Qt, configure and build Qt for the Raspbian environment. Let me take you to the remote machine where I had put it together. So this is my work folder where I had put things together. The file, .img file, I obtained it from the web, and then I have mounted it. Let me show you the tree structure for this directory. I mounted that file to a folder called rpy-rootfs. There it expanded into the image of the root file system. In case of Raspbian, I had to make one deviation. This image file system, this .img file rather, is meant for flashing it on the Raspberry Pi device. It is not meant for development. So after mounting it on a local folder, I had to run this sysroot relative links script to make sure all the header files and the libs are included in that rpy-rootfs folder so that I can utilize that folder for my development effort. And then what I did was I also obtained the tool chain, which is inside the tools folder. And I had created let me show you the shadow build that I created. So this was the configure command line option that I had used. If you notice, I have specified in the -device option the cross compiler path. That's the tool chain I have on my system, and in the -sysroot I'm specifying where one can find, or where the configure can find, the header files and the libs for the development, required for the development. And what I usually do is I create a shadow build folder so that when I make build or when I configure build, I do not clutter the original Qt sources. So I have created this shadow build folder in which I have the result of the compilation. And after configuration and compilation, I got everything set here. That's what is a result of building Qt and installing it in the development environment. Then I had to set up the device. I haven't included the instructions to enable the networking on the device and the SSH daemon, but that could be easily found on the web somewhere. For the SSH, the reason why we need the SSH daemon is if you want an ability to deploy an application from the Qt creator, this is the missing piece that you would need to be enabled when you are running the Raspbian image or any other image on the device. So to set up the device, what I had to do was, as I have mentioned, enable the networking interface, then enable the SSH daemon, and then I have to physically copy the Qt libs to the device. Now there are different ways in which you could do it. You can copy it to the IMG file and then flash the IMG on the device, or you can use scp or rsync command to do that. Then I'm going to show what else you need to do. So till this point, we have taken care of configuring Qt for the Raspbian and building it. And now we have to start using it. The one way we can use it is to set up the Qt creator to be able to deploy it to the Raspbian. I had done that too, and I would show you an example shortly. So this is, I'm remotely accessing my Linux development environment. So what I did was in the tools options, I had to first create a device. I'm not going to walk you through the whole device creation process, but I will show you where I started it. So you go to the devices tab, then you choose this add button to do it. The name could be any name. Since I'm doing it for Raspbian root file system on rpy3, that's the name I've chosen. Then you have to pick the host name and the username and password on the device. After you have done this, you can run the test program to see whether there is a connectivity with the device, and once that is confirmed, you are a bit set on the setting up the device part. Now what remains is how to integrate the tool chain and the build result in the Qt creator. So now what we have to do is go to the build and run tab. There I have already set up this Qt creator, so I won't go through all the steps there. I'll just show you what I did. So I added a custom compiler and I specified the path of the G++ file that's on my host machine. I have to also specify the mech path that I'm going to use. I really don't need to specify a C toolchain, but if in case one writes a simple C file, you can put this to use. After setting up the compiler, then I had to create the Qt version. What you do for this is you locate the, you say add and you locate the QMake file that you had built. So if you see on my host machine, I had installed the result of my build in the rpy rootfs under user local qt5. So I located my QMake from there, and I'm all set in terms of the Qt. Now I go to the kits part. So what I did first was the compiler, then the Qt version, and now I have to put them together and make a kit which I can use to build my application, which I have done here. I gave it a relevant name. I have to specify what device type this would be targeting to. So I won't be using others because they are very specific to the boot to Qt image or the Android and the QNX device. And since my Raspbian image is none of them, I have chosen a generic Linux device. And if you remember, in my earlier attempt, I had created a device entry here. I would choose that while creating my kit. That's been selected here. What it means is when I build and when I want to deploy, it would be deployed to this device. Sysroot was auto-picked. I had to specify the compilers, which I had set earlier. Then I had to also specify the Raspbian version, then the devices make specs, and I'm now all set. So what I did was first I created the device, then I went to the build and run. I set up the compiler, the Qt version. I had to do it manually, and then I created a kit manually using whatever I prepared in the Qt versions and the compiler. Now I'm all set. I have opened a sample application. Unfortunately, you won't be able to see the result of the deployment, but what I could show you here is amongst all these kits which are available to me, I chose the Raspbian, the one that I created. I chose it, I chose it as the kit against which I want to build my application and run it on. So if you look at the run tab, you would see that it would deploy the files using the SFTP protocol onto the target. As I said, you may not be able to see the application actually run. You won't be able to see the UI, but you would see the result. So now I do the usual stuff, run QMake to parse the .pro file, rebuild all. In the compiler window, you would see that the right toolchain is being picked and all my CPP and QML files are being processed. The right libs are being picked here, and that's all set. So no errors. That means I can deploy my application to the device. So here you are seeing the console messages that indicate that you are able to deploy it to the device. As I said, you won't be able to see the application UI running on the device since I do not have a camera pointed to it, but you could see that it was able to copy the files and run successfully without any error. So that's pretty much it about setting up Qt for any non-Yocto build environment. And I'm going to run through some of the files here. So I'll show you what were the changes I made. So this is the qmake.conf file I mentioned. If you look at the path of it, it's in the make specs devices. I created a copy of the existing file, existing folder, and renamed it as a Raspbian Pi 3 for now. And the changes I had to make here was the OpenGL file names. Now, in the earlier versions of Raspbian, the OpenGL file names were very similar to what the standard OpenGL library is, but in this variant of Raspbian, the file name had changed. One of the options I could have tried is I could have introduced a variable inside the existing Raspbian qmake.conf and would have specified it and would have used it here. But for this use case, I decided not to do that, and I may do it when I'm going to check in my stuff. But this is the qmake.conf file I was talking about. If you see here, I'm choosing my own variables, considering where I would find the OpenGL files in this Raspbian image, and this is where I can specify what other compiler or linker flags I want to choose. So that's pretty much it about building Qt on a non-Yocto build environment. I would also just walk you through some of the other files. So if you look at this devices folder, you would find support for most of the devices. So it's very less likely that you would have to spin something of your own. But just in case required, what you have to do is choose one of these folders which is very close to the environment that you are working or the device that you are working, and then start with making a copy of it, and then adding your specific changes. And once you are done, then you can think of merging it back to any of the existing ones. So that's it on the building Qt with the non-Yocto build environment. Now I would move on to discuss some of the options we have on choosing the graphing backends and the input handling choices. As you know, it's not easy to play with these different windowing system interfaces. Like for example, even if you had to render a simple OpenGL, you would have to write a piece of code wherein you create a window, then opt in and handle to the window, then opt in the right surface to do the OpenGL rendering on. And on different platforms, you would find different APIs to do the window handling for you. I have listed some of them out there. And in some cases, in some platforms, you have multiple options. Like on X11, you would have GLX and EGL both. Thankfully, Qt takes care of all this headache for you, and it has provided different platform plugins that would help you set up the OpenGL context and create the window surfaces. So Qt has abstracted this for you, so you don't have to worry too much. If you remember the old Qt 4.8 days, it was a time like it was the old school way of doing things. So there you were creating multiple windows even on the embedded environment. It wasn't that likely, but there were situations where you were doing some kind of window handling. So back in Qt 4 days, we had our own windowing system, which we called as QWS. But starting with Qt 5, we don't need that anymore. With Qt 5, we removed the QWS support, considering the requirements for the new and the modern devices. So in that case, what we are left with is either we run it as a single process or a multi-process. And both these use cases are handled in Qt. When you are going to run the Qt GUI application as a single process, you have multiple choices there. Typically, you would be using the frame buffer or the KMS DRAM API. And as I said, this is abstracted from you. You don't have to worry too much. Most of the support would be already there, but if you have to make some changes, there are places where you can do that. And the multi-process use case is also handled. Either you use X11 or Valent. Qt provides support for both these by the means of the platform plugins. So that use case is handled as well. In the single Qt GUI application use case, these are the two most used options. There was one which was called DirectFP, but the DirectFP is not supported anymore, and that's why we do have the plugin, but if you want to get it working, there would be some effort required there. But fortunately, as I said, these two platform plugins meet most of your requirements. If you are looking for a 2D or 3D acceleration, EaselFS is the choice. So EaselFS is the platform plugin that uses Easel and OpenGL. Recently, we have also added a support for OpenVG. So if you have a EaselFS platform plugin enabled for your platform, you could run widgets and Qt Quick 2 applications. Qt 3D is possible if you are using OpenGL, not if you're using OpenVG. And the Linux FP is a pure software rendering engine. So there you could run widgets and Qt Quick 2, but with the software backend. And when you run with software backend, you won't be able to leverage some of the OpenGL APIs that we use. For the multiple Qt GUI applications, and before I go there, I want to clarify one more thing here. So when I say single Qt GUI application, what I mean is you can also run other Qt processes or other processes, but there will be only one process or one application that would be rendering the UI to the screen. There cannot be multiple UI applications. So you could write a Qt backend applications which do not necessarily use any of the EaselFX or Linux FP plugin. On the multiple GUI applications requirement use case, you have Wayland and X11 as plugins. Obviously, you would need these to be supported on your platform. So if you're planning to use them, make sure that the Wayland server or the X11 server is available on your platform. If you're using Wayland, you can use a Qt's compositor as one of the options, or you can use the Western app, or you can spin one of your own. In either of the cases, all your clients, the Qt applications, they would be using the Wayland platform plugin, and that supports Easel plus OpenGL, and you can run widgets, Qt Quick or Qt 3D applications there. For X11, there are two choices: Easel plus OpenGL, typically on the embedded side, and GLX plus OpenGL on the desktop side. You won't typically run GLX on the embedded side. And when you are using the XMD plugin, you have an option of running the widgets Qt Quick 2 or Qt 3D application. So let's go through the EaselFS backend a bit. So as most of you know, Easel is a API, is an abstraction that gives you access to the window surface for a native window. So on a given platform, you can create the window, the native window, using different means. Many times there are these vendor-specific structs which are on top of FPDF, or there are some system compositors like the one exposed by Raspberry Pi. So you would use those APIs to create the actual window instance, but then the Easel would act as a interface between the drawing API and this windowing API. So Easel would make the surfaces available to the drawing API, and that's what we are exploiting in the EaselFS. As FPDF is one of the options, and another option which is more popular these days is the kernel mode setting and direct rendering manager. Now this is getting into being a standard method of doing things on the embedded platform, specifically on the embedded platform. It has two variants to it. One is the buffer management approach is done using the generic buffer management mechanism, and there are certain platforms which also use Easel device and Easel streaming option. Those are NVIDIA devices. So on the frame buffer, what we do is we get access to the /dev/fbx device, and we use a bunch of octals to control and obtain some information from the device. Now, in case of FPDF, when you are using the Easel and OpenGL, the Easel implementation will actually access the device and Qt layer is kept abstracted from it. In case of non-accelerated devices, which is typically used when you use Linux FP, the Qt itself would write to the /dev/p0. It would be utilizing the software rendering there. But in case of Easel, if you are using FPDev along with Easel plus OpenGL, Easel would make the surfaces available to the OpenGL engine. If you are using this FPDev, there are some specifics or rather I should say there could be some specifics for some of the platforms and drivers. The only problem with this is with this approach, using FPDev is that the multi-screen is not supported. And even if it is very vendor specific, and you won't be able to dynamically change your screen for your application. So Vivante is one such exception where you can choose which screen to target the app to, but you won't be able to change it at runtime. And FPDev doesn't give us enough capability to discover what are the multiple screens attached and then if the application can utilize them. So that's one approach used while implementing EaselFS. You really don't have to know too much about it unless you are going to spin out your own version of EaselFS or going to add a hook to EaselFS. And the next approach is using the KMS and DRM API. As I said, this is the most supported API these days on the embedded Linux environments. Qt used to have a separate plugin in the earlier versions of Qt, which was called as a KMS platform plugin. But we have recently replaced it we have split it into two, and we have two EaselFS backends for that. One is EaselFS KMS, and the other is EaselFS KMS Easel device. EaselFS KMS uses the generic buffer management API, wherein the KMS underscore Easel device uses the Easel streams that is supported on NVIDIA. If you want to look some additional information on this, there is a link out there where you can learn more about how you can create the JSON files to tell how to utilize these multiple screens and how you can set different modes on the different screens. This approach of using the KMS and DRM in EaselFS has some limitations, but we haven't seen that being a hindrance so far. But it doesn't allow you to exploit the different graphic planes exposed by DRM. So those are the features we haven't added yet. As I said, we didn't require them to, but with some effort, those could be added as well. I'm just listing out the different EaselFS backends that are available to us. As I said, with the recent approach, the focus is on KMS and DRM, utilizing those APIs in implementing the EaselFS. There are two variants to it. One uses the GBM, other uses the Easel stream. And we also have a few FPDev specific implementations. As you could see on the right-hand side, we have this EaselFS Mali Viv implementations. So as I was saying on the earlier slide, there are some vendor-specific FPDev glues, and that could be found in the Vivante or Mali or PowerVR FPDev. I don't think we maintain the PowerVR FPDev implementation anymore, but since the more modern approach is to resort to using DRM and KMS with the GBM, and that's what you would find on the recent PowerVR systems, especially Renesas and the Intel NUCs. A DRM KMS implementation which uses Easel device that's available on the NVIDIA platform, and there is a proprietary system compositor implementation which is specific to Raspberry Pi. You can use any of these existing backends to implement your backend. But I believe most of the use cases have been covered in this option 2, where we are using DRAM KMS with GBM. And now we would talk about how to deal with different input choices that we have on the embedded platform. Typically, we don't have to really address the keyboard aspect, but there are some devices out there which need the usual 101 keys keyboard to be supported. So we have those plugins available in our implementation, but it's very rarely required on the embedded side. So when you are using the XAB and Valent plugin, you don't really have to worry much about this input handling and input routing mechanism, because that would be typically taken care by the compositor in case of Valent and the X server in case of XAB. But when you are using EaselFS or Linux FP, then you would have to look into this. That doesn't mean that you have to really implement anything in your application, but you would have to look after these plugins when you are building or configuring your Qt. So for inputs, we have these two stacks available. EVDev is the primary device that we use, and we have some implementation for those, for the keyboard, mouse, and touch handling. So that's one set of input handler. Lib input was added later in the community, I mean, not in the Qt specifically. But so when the lib input was added, we also created our own plugins to process lib input. Now this would be chosen, like whether to use the Qt provided EVDev handlers or lib input would be chosen at the time of configuration. So you would have a configure flag for that, and you can also choose which one to set up at runtime when you would be actually running the application. I'll talk about that in the next slide. In either of the cases, whether you are using EVDev or lib input, we have seen many complaints or issues on those, wherein people want to know how to support the hot plugging, because that's what they see missing sometimes, but it's not because there is something lacking in Qt. The support for that is already there in the Qt code. What you need to ensure is when you are setting up your root file system or the build environment, make sure the lib UDev header and libs are available. When you configure Qt, you can take a look at the configure log to figure out if these were selected, and if not, then please make sure that the header files and the libs are available when you are configuring and building Qt. So that would take care of the hot plugging aspect. As I said, the support for this input handling is built into both EaselFS and Linux FP plugins. But if you want not to use lib input, there is this environment variable that you can expose. And thankfully, we have added a logging mechanism throughout the Qt plugin and throughout the Qt code. So there is this variable called Qt_logging_rules. It has different options. So if you say qt.qpa.star true, it would provide you log messages for both inputs as well as graphics. There are options. There are further options into that .qpa, which are present in documentation. So if you go through our documentation, you would find out what other options you have there and what kind of messages you can see. So you can confine your log to the specific messages. For example, if you don't care about the graphic log, you could say qt.qpa.input.star. That would help you determine what input handler was chosen, what input handler plugin was chosen, and what kind of support you have. As I said, as a means of troubleshooting, both these, the EVDev and the lib input plugins, they rely on these endpoints /dev/input event 0. They could change from system to system. These are most of the times these are really standard, but if they change, you would have to make a change by specifying an environment variable. This is also available in the documentation. The link to the documentation is at the end of the slide. So if you ever run into any issues with the input handling devices, you can go through that link and find out different means to the troubleshooting. And as I said, to support the hot plugging, you would have to have the libudb libs and header files. Now there is this second option as well, tslib. It's not relevant these days. It's more overused in the old times when you had to deal with resistive touchscreens and you didn't have this drag and drag support. If at all you are dealing with those kind of devices, then you would have to use tslib. As I said in the documentation, you would find instructions on how to enable the tslib if you have to. And you might have heard few blogs in the past when we introduced Qt Lite. I would just touch upon a few aspects of Qt Lite. Qt Lite is a what is Qt Lite? So Qt Lite has two parts to it. One part is refactoring the code so that we can trim what we want, and the second part would be the tool that would allow you to do that. So the first part existed in the past in one or the other form, like you could skip the entire module by saying -skip. You could remove a feature by saying -no feature, minus the name of the feature. So these options were there in the past, but then to figure out what to choose and what not, you have to go through different files and figure out what are the means available to you, and then you would have to understand the dependencies. Those were documented, but then suppose you decide to not include a certain feature, you would have to realize that what goes away with it, and then accordingly take care in your code. So that was a bit cumbersome, and after we decided to focus more on this, we also added some new features which were missing in the part one of the solution. But we also introduced this part two, which is the actual GUI tool. I have added a screenshot of that tool for your reference here. I would also show you an instance of it running. So if you remember, I did two shadow builds for Raspbian. One was open source, another was the commercial. Please note that this Qt configuration tool would only work with the commercial version of Qt. It won't work with open source. So these are the options I was talking about. Some of them were there already present in the earlier versions of Qt, but they weren't supported with a GUI like this. So if you see, if I choose the QML profiler, it says these are the required features, like local server, QML network, and all that. So if I choose to disable a few things here, so for example, I have taken the big codecs out and codecs and icon v out, and in the quick side, I had removed few things. I could also remove some of the widgets if I don't want them. Like if I already decided what my GUI would look like, and I know what I'm going to use, I can remove what I'm not going to need. For example, in the Qt Quick here, I have removed the canvas and views and particle and all OpenGL effects because in my application I'm not planning to use them. So after I create this, after I make my choices, this GUI tool is going to help me decide what I have chosen and what I'm going to miss. So if I make any incorrect choices, it's going to help me identify those. After I make those changes, I'm going to save this file, and I'm going to use it while building Qt. So here is where I had built the Qt. And here is an example of that OPT file that was created. It picked up all the options that I had specified on the command line myself about skipping what modules I want to skip, and on top of it, it also added this no feature based on whatever features I deselected from the build. And then I just say reconfig, I say configure redo, and all the settings that I have made in this OPT file were chosen. Before I use the Qt config tool, I have to configure my Qt sources at least once, so it can pick up the configure.json file and then allow me to make this selection. And then just redo the configure and everything will be taken care. Let me see if I have an example here showing what we got as a result of that configure. So I'm going to list the contents of the Qt base in this folder, which was the Qt latest commercial. So that's the size of the files in my Qt latest commercial, which is a stripped down version. And Qt latest is an open source version where I didn't do any optimization or removing of features. So if you could compare, for example, I didn't choose a Qt concurrent feature in my commercial shadow build, so that lib is totally absent. I stripped down some features of Qt core, so my Qt core reduced by 0.5 meg. Similarly, if you look at the Qt GUI, if you look at Qt widgets, there is some reduction of 300K out there. So you can play with the different features and further strip down the Qt libs. And obviously, when you do a static build, you are going to reduce a few more bytes there. So that's about using the Qt Lite configuration tool. These are the 3 files that are created for you. The command line, so config.log would contain the command line that you had used to do the configuration. Config.summary would give you the brief status of your configure option. And config.opt is the output file that is created as a result of running that tool. And this is where you would find the command line options that are used to strip down the Qt bins. You can directly use the config.output while configuring, you can really use the contents of the config.output as well to do the configuration from the command line as well. Like if you are going to create a script or you want to edit something in the Yocto layers, you can use the result of this config.out. And then on the last topic about adding the Qt recipes to your own Yocto build, what I did was I created a build for the Raspberry Pi, and to do so I had cloned, amongst other repos that I had to clone for the Raspberry Pi, I also cloned MetaQT5. Then in the MetaQT5, the Qt5 recipes are in the recipes Qt5 folder. That's where you would find what version of Qt is being pulled and what are the different packages available that you have to enable if you want to. Then I edited the BB layers. Now here I'm not going to go through all the steps required to set up a Yocto build because that's a session in its own. So here I'm assuming that you have some familiarity with Yocto. So to begin with, you would opt in all other Yocto layers other than MetaQT5, and then when you set up the build environment, you would modify the bblayers.conf file to add the MetaQT5. And based on what, if you are going to create a development image, you would have to add this variable extra image features and add these packages so that you get an ability to create a development image plus you would enable a SSH server on the device so that you can use a Qt Creator to deploy your application from within Qt Creator to the device. And to create the toolchain, you will use the bitbake command with the target as meta toolchain Qt5. So this comes through the meta Qt5 layer. There is a recipe out there to create this image. So the meta toolchain Qt5 would create the SDK for you. It would result in creating a shell script which you run on your host, and it would set up the development environment for you. You would have to then follow the similar steps that I did earlier for the Raspbian image to set up the Qt Creator to utilize the result of this bitbake operation. And you would also use, so I have another example here. Let me open up the no, this is not the right one. Yep, so hope you're seeing the right. Yeah. So this is that script. This is that recipe that pulls in the SDK. It inherits the populate SDK and populate SDK Qt5. This is part of the meta Qt5. You don't have to do anything else here because that everything has been taken care for you. The only part where you would need a modification is I had created this example meta RPi layer. Let me share that. So this is the bblayers.conf I was talking about. I had added the meta Qt5 layer in here. Have created my own meta RPi layer that would pull in the recipes from Qt5 and help me create a image that would contain Qt libs. I will show you an example of one such file. And in the local file, this is the variable that you would have to add those extra image features which I had listed earlier. And let me open and this is a simple recipe I had used in that meta RPi layer, which includes what are the different Qt components I need. But prior to that, I'm inheriting one of the other images, and then image install is the variable that would choose what Qt components and Qt modules would be included in the Qt5 basic image that I would be creating. So I would run the bitbake command one more time with Qt5 basic image as the target, and that is going to create an image with Qt5 libs in it that I can deploy to the device. I think I'm at the end of my presentation now. So if you have any questions, I can take them now. These are the links that you can go to get some additional information on the topics that we discussed today. We have a few minutes left, but if you have any questions, I'll be happy to answer. So one of the questions is, do I have to write my own EaselFS implementation? The answer is that's very rare that you would require to create your own EaselFS implementation. But if you have to, for some reason, you would typically use one of the existing EaselFS plugins and add your hooks, add your implementation to that. But as I said, most of the scenarios have been taken care. So it's very rare that you would have to write your own. And then there is another question, what's the difference between Meta Qt 5 and Meta Boot to Qt? So Meta Qt 5 is a layer that was created by community, but very recently, probably since a year ago, Qt company is also contributing to that layer. We make our releases every 6 months, so we push our changes to the Meta Qt 5 layer every 6 months. So to an extent, it is up to date from our side. But the Meta Boot to Qt layer isn't available as an open source, isn't maintained by the community, it is maintained by the company. And what it contains, it has some additional tools, some additional recipes that help you do some debugging. So there is an option. There is a question: what's the difference between -device option and X platform? So in the earlier days, X platform was used to specify the target platform. That option can still be used, but I would like to point out one issue with the question. Maybe you were wondering about the -device option and -X platform, because -device option is a way to set the variables set the values for the variables that are used inside qmec.conf. So the question should be the comparison between -device and -X platform. They are very much the same, but if you are targeting for the embedded devices, we suggest you create your mexspec qmec.conf files inside -device folder. And if you're utilizing the QMX from there, you would typically use the -device option. But if you're using the targets from the upper layer, you would use the X platform.
Well, thank you very much for your presentation, Shrikant, and everyone for joining. If you have any additional questions, please contact us at the URL provided in the screen, qt.io/contact us. Again, we'll be sending the presentation recording to you, as well as the presentation slides in the next 2 days. Please do share it with your friends and family. And again, feel free to contact us at your convenience. Thank you.